Okay, we're going to talk about post-quantum cryptography and really the hybrid methodologies that we've been asked to put into place in the industries that security systems are protecting. So there's a lot of marketing material that kind of has a little hype going on and a little scare tactics going in. So we'd like to distill that down and kind of level set on what has been so far a very public roadmap for quite some time. Let's get started. First, let's talk about quantum computing, or a quantum computer and what it really is. Quantum computer is not analogous to what you have at your desk, nor it is analogous to the servers or high-performance supercomputing industry. A quantum computer is a very specific system with very specialized hardware to handle very specialized mathematics. So if we break it up into two pieces, we have a logical qubit, which is, for this discussion, analogous to binary, 0 and 1. But then we also have hardware qubits, how we store a logical qubit. Now, a logical qubit is actually a vector state. So each qubit has its own vector space. Now, as you add more qubits in there, you can start to understand that if I'm storing a vector space or a vector state, I can start to scale this information exponentially because the vector state lives in this complex state space, which is actually able to store complex numbers. Now, when you take that piece of information and then you think about a quantum wire, which is that vector information existing in a quantum state space, and you apply a quantum gate to it, which also can be a complex number, you start to understand the implications of what kind of mathematics you could actually prove with a quantum computer at sufficient scale. That's just the math part. On the hardware part, you have a hardware qubit, and that is how we store that logical qubit in our physical reality. How that works is depending on what hardware you're trying to store it in. There's been a lot of different methods for storing qubits. The problem with all of this is the better the qubit for storing information, the harder it is to read. The better we can read a hardware qubit, the weaker the state is to store that information. So we have this double-edged sword of the easier it is for us to extract a qubit's information, the less relevant that data is going to be. I say relevant because there's also a probability factor, and that's where error correcting qubits come into play. This has actually been what has accelerated recently over the last 5 years. So we have a lot more improvements in how we can do error correction on the information stored in a qubit, which is why this is suddenly a big discussion. With all that information, you can now see that it takes very specific discrete mathematics input into a very specific type of computer that then has to have the amount of probability to give you the correct answer when you read it, which makes this a very complicated machine, specifically for trying to break encryption. So what this means is you're not going to have some kid at the coffee shop with a pocket quantum computer ready to hack your bank accounts. That's not how this is going to work. Nor are we all going to wake up one day and all the encryption is disabled because what's the point? That's not how this works. How does this work? So quantum computers are spooky to a lot of us because A, we don't understand the complexity of the mathematics, but we've heard about algorithms that could potentially break our current encryption standards. So in 1995, we had Dr. Peter Shor come up with actually a series of algorithms that are able to factor large prime integers very efficiently, which would render our RSA, Diffie-Hellman, elliptical curve, Diffie-Hellman, and then Dr. Love Grover's algorithm solved basically brute forcing symmetric encryption at a lower bit strength. So it doesn't outright break it, but it's going to be able to solve the problems much more efficiently than a classical computer. No hardware really could affect these algorithms into quantum relevance for modern cipher obsolescence until, say, the last 5 years. We've really made a lot of, not me, the industry of quantum computing has made a lot of strides over storing logical qubits over the last 5 to 10 years. This was really put into a discussion point when in 2015, Dr. Mikhail Mosca basically told us there's a 1 in 7 chance that some fundamental public key crypto will be broken by quantum by 2026. He then came out and said there's also a 1 in 2 chance of the same thing happening by 2031. That 2031 date is what has everybody really concerned. with some of the advancements to the hardware and quantum computing, even that's a wavering date at this point. Our international PKI community deadlines are for quantum secure match that. It's not a coincidence. At the same time, when Dr. Mosca discussed that 1 in 2 chance of 2031, he also came up with an inequality theorem to help us prepare or create a date and timeline to be quantum ready for this cryptographic relevance of a quantum computer. So he came up with the formula of D plus T is greater than QC, or the duration of time you have to keep your data secure versus the time it's going to take you to upgrade your systems to be cryptographically secure from quantum computing. If that's greater than when a quantum computer becomes cryptographically relevant, you have a problem. Let's take HIPAA and FINRA for an example. So HIPAA doesn't necessarily have a requirement for all their documentation, but for things like release forms, consent forms, they have a 6-year keep this secure. So you have to have governance around those forms and keep them available and safe and secure for 6 years. FINRA has a similar thing for security exchanges for their advisors, where you have to keep that financial data secure for 6 years also. So we're going to take that 6 years that HIPAA and FINRA have to adhere to. That's our D, or the date that we have to keep that data secure. Now, we've been looking across the industry, and it's going to be a pretty heavy lift to migrate all of our systems to quantum-resistant cipher suites. You have to think of not only web traffic or certificates that we're creating, but you have to think of firmware and everything where it's using one of these modern-day standard ciphers. That's that T time. So we're seeing 3 years, 4 years, 5 years as expected roadmaps for being fully compliant. So if we have 6 plus 3 or 6 plus 4, 6 plus 5, and we have this 2031 date, we definitely know that 6 plus 3 is more than 2031 because that's a year. We know that 6 plus 4 is way more. We know 6 plus 5. So we have this overlap of when we're going to have our information secured for quantum computing versus when a quantum computer would be able to decrypt that information. That is what we would consider the industry uh-oh moment. That seems okay. We have a plan. So what's the issue? Why is everybody kind of freaking out about this? Let's find out. What we're seeing are nation-state activities or state-sponsored adversaries. Instead of creating malicious output, they're setting up listening posts. And when you set up a listening post, you're kind of curious about what they're listening to. So we know one example is Canada Telecom had an exposed infrastructure bug in some of their hardware that was taken advantage of by one of these state-sponsored adversaries. That state-sponsored adversary set up a GRE tunnel and started pulling data. Now we know that data is secure, so what's the issue? They're just pulling in whatever they want. Why? Because the telecom's an aggregation point. An aggregation point is pulling in a lot of data from a lot of different places. So this state-sponsored adversary, we don't know what they're targeting, but they have the ability to target a lot of people. Where's this going? This is where you've heard of harvest now, decrypt later. So if I can harvest all this data now, I can store it. And when a quantum computer becomes cryptographically relevant, they can then take that stored data and decrypt it at their leisure. This is a huge concern because it does bypass Mosca's inequality theorem. It doesn't matter if we have that overlap or if we're really, really prepared, the data could be stolen now. Or the data that's already been stolen over the last decade could just sit there quietly in storage until they're ready to use those quantum computers. Now let's also take a pause. Remember how complicated those quantum computers are. The reward has to outweigh the complexity of implementing nefarious quantum computing. It is a heavy lift and requires extremely smart people and a lot of money. So this is definitely where you're looking at nation states. And those nation states are going to be looking at very large targets. Telecom service providers, federal healthcare, financial manufacturing, critical infrastructure. Those are all the industries that really would be prime targets for somebody with the ability to implement a quantum computer for these uses. So here's where this gets cool. So I'm going to paraphrase Chuck Heron, F5's field CISO, in that this is one of the few times the industry has actually been prepared to handle this migration before it happened. We've known about these algorithms. I mean, quantum computing and the cryptographic potential of it has been known since the 80s. And the hardware has been moderately relevant for 15 years, really in the last 5 to 10 years, like I'd said earlier, but we've been aware of it. This is different from API security, where APIs had been all over the place, and then we started figuring out ways to secure it. Same thing for web app firewalls, where we had applications everywhere and we were trying to use just regular firewalls to protect it. Didn't work. So the security usually came after the problems existed. This is the instance where this is not the case. It's reversed. In 2016, NIST, the National Institute of Standards and Technologies, put out a call for papers to develop quantum-resistant mechanisms, specifically to solve this. And they've gone through several iterations. There's been 4 rounds so far, at least for the US and NIST. There have been similar processes for other countries in the EU and then individual countries. And so at least for the US, NIST established FIPS 203, 204, and 205. 203 solves for our handshaking, 204 and 205 solve for our digital signatures. And now the NSA, who used to have Suite B, is deprecating Suite B, which was based off elliptical curve cryptography, and they now have CNSA 2.0. And this sets what NIST provided. It sets the bit strength of those and which specific mechanisms they're going to use for top secret, important documentation. So if we take those two, we actually have a roadmap for the US, and other countries have similar roadmaps for their own cryptographic requirements that exist. Why do we call it hybrid? Is because we're still allowing classical cryptography to coexist with these quantum secure cryptographic methods. Whereas FIPS 203 replaces one of the older FIPS, but it's actually talking about a key encapsulation mechanism. And that pairs or bolts on to the side along with these other systems that then replace, like an MLDSA, which is DSA, but it's module lattice, which is quantum secure. So we've added all these modules in there to allow cipher strings a quantum relevance or a quantum secure relevance while still allowing classical cryptography to coexist at the same time. We're basically creating a redundancy pair to make it difficult for any one system to figure out any of those cryptographic methods. Now, it's hybrid because of that, but we also know that there's a lot of other countries that are doing their own thing, either in the same algebraic family as what we have used, the crystals Kyber and crystals dilithium, along with Sphinx Plus and Falcon. There are other mechanisms that other countries are using. China and South Korea have actually standardized on their own completely different set of algorithms. So, how do we migrate? We migrate at a fast marathon. This is not a sprint, but we have done this before. So we don't have DES anymore. We don't have triple DES anymore. We migrated off those. We don't have SHA-1 anymore. We migrated off that. We saw the annoyance of having to increase key bit length in order to get better security, so we implemented ECC. We've done this in bits and pieces. And we have the MITRE Network's Post-Quantum Cryptographic Coalition to actually give us a migration strategy on how to do this. Now, this is basically just good project planning, but they've detailed it out specifically for cryptographic teams in order to identify and then create a plan of attack, a budget, because this will cost us money, either hardware, software, developer time and recompiling things, we don't know, but they do have a strategy. Now, the key thing is going to be at the end of the strategy as we migrate over to these targeted dates that NIST has set forth and the NSA has set forth for the US of 2030 to get in before that Mosca inequality date of 2031. Evaluating and monitoring how successful we were is going to be very important because we're going to do this again. Some of the algorithms that we are going to be using are not necessarily as performant as they could be. So we do know there are better ways to do it, and that's the migration strategy. So we know we're going to probably have to do this again. So it's best to get that cryptographic agility muscle in place and prepare. I have another video that will actually detail in a little bit more into what the cryptographic string would look like where the potential problems are, how we solve for those. We'll talk a little bit about OpenSSL, Boring SSL, how they're solving for that with the OQS libraries. We prepared labs for the practitioners that want to kind of go through this and just see how they would build these types of keys and certificates in a quantum resistant scenario. If you like this video, do whatever buttons you want to do. I'm not your mom. And thanks for watching. Mahalo.